Welcome everyone to this week's autonomy talk. This week is a special one in that we have, well, a special guest I will tell you more about later, but also featuring between two seminar series and two labs, my lab here at MIT and Simon Calvert's lab at U Delft. So first, Simon will introduce the lab as well as the seminar initiative they have. Then I will introduce the speaker of today, Professor Marco Pavone, and then we will proceed as usual. But yeah, to maybe start, Simon, go ahead.
Yes, sure. Thank you very much. So yeah, it's great that we can do this as a joint webinar today together with Autonomy Talks. So my name is Simon Calvert. I'm Associate Professor at the TU Delft, also Director of the Automated Driving and Simulation Lab, ADAS lab for short. And then basically, just give a really short intro because we want to get on to Marco. So what we do is collectively we're looking at many of the challenges that exist with automated driving and trying to bring them together from internally within the Delft as a outward connection point for automated driving within Delft. Also though as a external collaboration effort within both Europe and also internationally to see how we can connect more of automated driving research, because I think most of us agree that by creating synergy across all the different domains and subdomains that are connected to automated driving, we can actually achieve much more. So this is part of our initiative there. And part of also the knowledge exchange is this webinar series that we started last year. So it's great that we can do this together with Autonomy Talks today. And yeah, we're looking forward to seeing what Marco has for us. So that's what I have to say today.
Thank you so much, Simon, and I agree. The more initiatives like this one, the better. So, as I said, today we have Professor Marco Pavone as a speaker. Marco is an associate professor of Aeronautics and Astronautics at Stanford University. There he directs the Autonomous Systems Lab and the Center for Automotive Research. And also, excitingly, is the lead of autonomous vehicle research at NVIDIA. So he translates research also in real life in very exciting applications. Something about Marco. Marco received his Ph.D. degree in Aeronautics and Astronautics from MIT. And before joining Stanford, he was a research technologist within the Robotics Section and NASA JPL. His main research interests are in the development of methods for analysis, design, and control of autonomous systems, focusing on self-driving cars, autonomous aerospace vehicles, and future mobility systems. Now, this is the official introduction. Marco has been a mentor and a role model for me for many years, and he will continue to be so in the next few years. And I'm really excited to hear about his talk because to me, he is really impressive in that he's super broad. As you will see, he works all the way from single cars to fleets, from vehicles to aerospace vehicles to soft robotics. So it's a very large portfolio, but also extreme depth. The contribution he has made over the years are really impressive for the depth and the advances he brought. And today he will talk about new efforts on foundation models for autonomous driving. This is a very exciting hot topic at the moment, and in his various capacities is leading the state of the art essentially for autonomous driving. And so we're very excited to hear more. Feel free to ask questions in the chat. We will monitor the chat over the duration of the talk. And without further ado, Marco, thanks again for making the time, and the stage is yours.
All right. Thank you very much for the kind introduction and for having me. So today what I would like to talk about is how large language models, vision language models, foundation models more broadly provide the opportunity to rethink how we develop autonomous vehicles and robotics system more in general. Now, the premise of this talk is that generative AI is forcing us to rethink the way we work and we seek out knowledge. For example, large language models can help us coding faster, as I'm showing here on the left. And the advent of such a technology is so profoundly revolutionary that some people are referring to it as the iPhone moment of AI. So what has been behind such a revolution in the field of AI? To a large extent, the main new technology that has been developed in the past couple of years that has caused this revolution is represented by foundation models, which has forced us to move from a paradigm of machine learning for specialized tasks toward a paradigm of general knowledge acquisition. Here I want to be a bit specific about what I mean by a foundation model. By foundation model, I mean a model that has been trained on broad data, typically at the internet scale and in a self-supervised fashion, and it can be adapted or fine-tuned to a wide range of downstream tasks. Examples of foundation models include large language models, vision language models, and video generation models. Indeed, NVIDIA on its website has a catalog of ready-to-be-used models you can play with if you are interested. Now, we're not there yet at a level where we have one single model that can be adapted to any training, any possible downstream task. But this idea of pre-training on very broad data and then adapting to specific tasks has been proven useful in many different domains, to the point that oftentimes when we play with these models, we often have the explanation why, wow, I didn't even know that this model could even do that. So it's tempting to say that AI, and in particular generative AI, makes everything better. So let's also apply it to autonomous vehicles. Well, not so fast. It is important to understand how generative AI and foundation models in particular could be useful to autonomous vehicles in the broader context of the state of the art in vehicle autonomy. Specifically, the AV industry is quite mature today, with very advanced driver assistance systems being productized as we speak, and companies such as Waymo offering robotaxi services, for example, in the city of San Francisco. And what has been enabling such a marvel of technology is the judicious incorporation of machine learning into the AV stack, for example, for perception tasks or for trajectory prediction tasks. But still, these very advanced technologies fall short, even today, in particular cases, in corner cases that, for example, require reasoning or more advanced understanding. For example, new deployment domains or optical illusions, for example, a truck that is transporting some traffic lights that might be mistaken as true traffic lights, thereby causing, for example, ghost brakes. Or on the bottom right, I don't even know what that exactly is, but essentially a giant mignon that is in the middle of the road, and the vehicle will need to understand that that is just an inflatable structure, so it will be okay possibly to push it out of the way. So here the point is that in order to address these corner cases effectively, the autonomous vehicle need to have some level of semantic reasoning capabilities in order to really generalize to unseen situations. So in this context, it's useful to make a parallel with how we as humans address the driving task. As humans, we bring to the driving task a lifetime of experiences, both from the driving domain, but crucially for the non-driving domain, which give us a strong semantic capabilities for reasoning. Well, the hypothesis is that analogously as for humans, foundation models that have been trained on a vast range of data, both from the driving domain, but crucially for the non-driving domain, have the potential to allow us to reason about auto-distribution domain situations, because in principle, they have seen everything, having been trained at internet scale. At least, this is the hypothesis. Then the question is, how do we access this generalist experience for AV applications? And the answer, as we will see for the rest of this talk, is in multiple ways. Foundation models can help with a variety of offline development processes, like, for example, improving auto-labeling pipelines or improving the way we do simulation and scenario generation, as well as improving the onboard software stack, either by enabling new architectures, for example, end-to-end architectures, or improving existing architectures, for example, through parallel algorithmic pipelines. The point here is that foundation models have the potential to really improve the full development life cycle of an AV system as opposed to specific components of it. Now, of course, there are concerns about the safety of safety critical systems such as an autonomous car that is empowered by foundation models. We are all familiar with the potential hallucinations of large language models. So fortunately, I will argue that we do have several tools in our bag in order to keep the AI in check. But at the same time, and this is a point that I will make toward the end of the talk, I will highlight how actually foundation models provide new opportunities to improve the safety of an autonomous vehicle, for example, by enabling the design of more powerful runtime monitors. So what we'll do for the rest of the talk will be to first provide some general considerations related to the development of a foundation model specifically for AV applications. Then I will discuss the key use cases in the context of both offline processes and the onboard autonomy stack. And then I will conclude the talk with a discussion about safety considerations. So let's start with the topic of how do we build foundation models. And to make sure that we are all on the same space, all on the same page, I will use multimodal large language models as an instructive example. Multimodal large language models are indeed one of the most prominent models in robotics and in autonomous vehicles alike. So essentially, a foundation model starts by encoding information into a shared latent space, which is represented by tokens. Tokens essentially represent units of information, such as semantic units of language, image, patch embeddings, vehicle state, action trajectory embeddings, and more. These tokens are then processed by a backbone, typically a large neural network, more specifically a transformer, in order to produce output tokens. And these output tokens are then decoded by leveraging task-specific decoders into modalities of interest in the context of robotics, for example, trajectories or actions, but also other modalities like, for example, maps, images, bounding boxes. We'll see later why in the context of vehicle autonomy, you might want to have modalities that go beyond to just simply outputting trajectories. Now, with these basic concepts in mind, so encoding information into a tokenized latent space, processing it through a backbone, transformer-based backbone, and then decoding it into different set of modalities, there are three main design choices to stand up a foundation model for autonomous vehicles. First, the choice of data. Second, the choice of the model. And three, the type of tasks that we use for pre-training and for fine-tuning. Now, in the context of robotics itself, data can be other data that is available at internet scale, typically language and videos, or images or intermediate representations. So basically, or point clouds. So all the typical data that we have available for a robotics stack. In terms of models, there are essentially two main classes of models represented by autoregressive transformers that are most popular for large language models, and the diffusion models that are most popular for video generation. And in terms of training tasks, we divide the training task between the pre-training on broad internet scale data and the fine-tuning. In the context of large language model, as the name says, the pre-training task is represented by the task of predicting language or text. And in the case of a video generation model, then the task is that of predicting images or videos. With understanding that the task of predicting language essentially imbues the model with some level of reasoning capabilities, if you will, because basically you're exposing the model to all sorts of logical pathways. While with the task of video generation, you imbue a strong visual representation in the model that is particularly useful, for example, if you want to add a planning head on top of it. Once we have pre-trained the model, so we have gathered general knowledge, then we can fine-tune the model on a diverse array of tasks, as I said before, in the context of robotics, for example, trajectory prediction. As I mentioned before, popular class of foundation models is represented by multimodal large language models, where the task is that of language prediction. We have worked quite extensively on multimodal large language models for robotics and autonomous vehicle applications. Here I show one example from NVIDIA where we use a multimodal large language model as an AI cockpit assistant that basically helps a driver to handle situations that might be confusing. Like, for example, this is a picture of a real road in Mexico, where we have this kind of a confusing arrangement of arrows. So here we have the driver that is driving in Mexico, is asking the model that runs on the car what is happening, and the model, which we call LADA, responds, well, please follow the arrows and switch to the opposing lane when safe to avoid oncoming traffic, as they indicate the traffic arrangement. So it so happens that in Mexico, in order to navigate such sharp turns, you're allowed to actually go on the other opposing lane and temporarily switch the direction of traffic. So here we have a multimodal language model that would act similar to a sort of software copilot, but here helping in terms of driving decisions. So we have been developing multimodal language models specifically for AV applications. More broadly, I'll get back to those later into the talk. Here instead, what I want to focus a bit more is on video generation models that represent another broad class of foundation models that are useful for AV applications. So here, the task is that of video generation. And what we've done as part of a large collaboration within NVIDIA has been to build video generation models for a specific task of predicting driving videos, essentially turning the task of video generation to a sequential prediction task, similar to a work by a company called Wave called Gaia 1. But we made several innovations to it, in particular, being able to predict videos from several different cameras concurrently. As I said, the idea is to turn the video generation task into a sequential prediction task. And here are some results where we prompt the model with the text of a video that we want to generate. So for example, a winter day in the city with a car driving past, a snowman built near a bus stop. And you see how the model, so the AI model, generates the videos for 3 different point of views. And as you can see, they are nicely synchronized. For example, you see the black car on the right-hand side that is coming into the view of the front center camera. Another example here. So all of these are AI-generated videos. You don't have to only generate 3 cameras. You can generate 6 cameras. So for example, here is an AI-generated driving video with 6 different synchronized point of views. Of course, these models are not perfect yet, so I would point your attention to what happens within the green square. So you'll see that something funny happens. There is a motorbike that appears and then disappears. Let me play it again. So you see this motorbike appears, look, and then disappears. Okay, so that's the problem of object persistence for video generation models. The model was not really exposed much to motorbikes, so it has been fixed since then. But just to say, and we'll come back to this topic later, that of course, even though video generation have a lot of promise, still there are some challenges in order to address them in physics-based applications. So the jury is still out in terms of which foundation model is best for which task. My hypothesis is that multimodal large language model that has been trained on essentially predicting language on reasoning tasks provide the best tool we have to date to reason through difficult corner cases, while video generation models provide the model with strong visual representations that can be very useful in order to build planning heads. Of course, video generation models can also be very useful for simulation. But my point here is that these models are really complementary to each other. It's up to a designer to decide how to best mix and match all these powerful tools. And I'll provide some more insights later in the talk. Let's move on and see how we can use these powerful new techniques in a number of different applications in the context of autonomous vehicle development, starting with offline processes. Now, neural reconstruction in the past couple of years has proved as an extremely useful technology for scene representation and for scene reconstruction. Here, for example, I show you one of our latest works called MNerve that allow us to reconstruct in a self-supervised fashion dynamic scenes by also allowing us to disentangle the static environment, the dynamic objects, and also providing optical flows, all of these in a completely self-supervised fashion. So the idea is that you record a drive, and then you train a model to regenerate the driving video, potentially from different viewpoints. So for example, here on the left, I'll show you some of the things that you can do with these reconstruction models. On the top left, I have an original camera log. So this was the video that was recorded by a test vehicle. And at the bottom, I show the re-rendered video from a completely new viewpoint. So as you can see, the visual realism of the trajectory of the video that is actually generated at the bottom is stunning. That's why there is a lot of excitement about using neural reconstruction as part of simulation technologies, because it provides one of the best ways to dramatically reduce the sim-to-real gap, at least from a sensor simulation perspective. Of course, you're not constrained to only generate images. You can also reconstruct point clouds, as the video on the right is showing. Now, all of this is great, but the important caveat with reconstruction methodologies is that all the agents in the videos are being replayed. So they do not really react to what the ego vehicle is doing. So this technology is really addressed the sensor realism gap, but doesn't really address the problem of modeling behaviorally the humans in a scene, which is important because, of course, interactions is one of the hallmark problems in the field of autonomous vehicles. So accordingly, in my group, we have also developed a range of data-driven models for humans, for example, bikers or agents, that you can pair with the neural reconstruction methodologies to address both the sim-to-real gap from a sensor realism perspective, as well as from a behavioral realism perspective. This is all great. The problem, though, is that generating simulations that are useful for AV development is hard. So essentially, you need to have artists or designers that set up, proper scenes and scenarios that allow you to stress test a system. And this is very time consuming, doesn't really scale much. And this is a setting where actually foundation models can help significantly. Specifically, in a recent work that we called LCT Gen, we explored the use of a large language model as a tool to generate a scenario. So essentially, the large language model receives a prompt, and then the large language model transforms this prompt into a structured description from a generative model that is then used in order to generate a scenario of a choice. And here I show how the different iterative changes you can make to an initial scene. And the most important one is the one on the right. So you see how we ask the model to speed up same direction cars in a scene. And the model moves, I don't know if you can see my pointer, but the model moves the blue car that is behind the red car to the other lane because it's dynamically informed. If you were to speed up all the cars and keep the blue car behind the red car, then blue car would rear-end the red car. So where this is even more useful is that now we have a technology whereby we can parse all the police reports about car crashes, and then turn those into reconstructed scenarios that can be used for AV testing. And of course, we can also fuzzy or randomize or add some generative elements on top of these scenarios to have even more scenes for stress testing. And why this is important is that one of the key concerns with using a simulation, particularly for stress testing, is how plausible it is, the scenario that you are generating. The fact that actually we ground generation into crashes that have happened in the real world provides, more more grounding for the credibility of these generated scenarios. Here specifically, we mine crashes from the NHTSA Siren database. Quickly, the way that the model works is by taking a prompt, feeding it through GPT-4 that provides a structured representation of a scene. A police report typically can be quite ambiguous. Then we provide some structure on top of it. And then we have a map retrieval framework that retrieves a map that most closely resemble what is described in the police report. And then we inject the map and the structural representation into a generator that finally generates the output scenario. We made some recent improvements to this pipeline through a work referred to as a ProSim, which is a much more flexible, promptable simulator, whereby we can add as additional conditioning elements goal points for the different agents. We can sketch trajectories for some agents to take if you're interested into that. And of course, we can also rely on text conditioning. Putting everything together, so basically neural reconstruction in order to address the sim-to-real gap from a sensor simulation standpoint and traffic simulation and text condition and the scenario generation. Here are the kind of things that you can do. So on the top row, I show a video, a real video, whereby there is a vehicle that is stopping at a stop sign. So it's doing the right thing. And then as a designer, we can ask the model, okay, so generate a new scenario that is very similar to the one that we have recorded, but where the vehicle that is in the green box now shows reckless driving. And that's what we do. And what we have in the bottom is, well, the animation in PPT was not great. The vehicle was supposed to be in the red box, but so what we have in the right is the same video where the AI model has removed the black vehicle and then is placed the black vehicle back. And then the black vehicle is now running through the stop signs without stopping. So let me show it again. So in the real video, the vehicle stops. And then in the AI generated video, the vehicle runs through the stop sign. And of course, we can generate all of these scenarios at a scale just through some simple text prompting or maybe sketching some trajectories. All right, so all of this is useful, and indeed we are using it, for example, NVIDIA as part of production. But again, there is a caveat. So reconstruction models, by definition, they reconstruct. So the moment that your vehicle under test is moving far away from the trajectory that was used to record a video, then you start observing artifacts. For example, here I'm showing on the right a situation whereby a vehicle decides to make a U-turn. There was a trajectory completely different from the one used to record the drive that was being reconstructed. And you see that we have a mess of artifacts and holes in the reconstructing scene. And it is actually a minor miracle that the end-to-end policy invent testing here can still perform in an adequate way. So the question is, how can we improve the generalizability of simulation by still keeping the same level of sensor realism of a reconstruction model? Well, I talked before about the video generation model, so it's tempting to say, well, why don't we use video generation models or video foundation models directly for the task of simulation? For example, at the bottom right, I'm showing you again a video that has been generated by a video generation model. Well, the problem, as I mentioned before, is that the video generation models can exhibit artifacts, like, for example, lack of object permanence, or, for example, some inconsistency in the environment that is being generated across time. So in a work that we're going to present at ICRA in a couple of months called the Dream Drive, we tackle this challenge by basically bringing together the best of both worlds, the world of video generation and the world of neural reconstruction. So basically what we do is to start from an image of somewhere in the world, like for example in Japan in this case, use a video generation model to generate a video of a driving scene, possibly with some artifacts. So for example, you see here that erratically the grass on the right turns from green to brown. That doesn't really make sense. But could be problematic specifically when you train end-to-end policies that might actually latch on to these weird artifacts. So what we do then is to feed this generated video into a 3D reconstruction pipeline. We have some works that we've done in my group, but of course, we can also use other works as well. And the idea here is that the 4D reconstruction pipeline enforce geometric consistency. And then once you have the reconstructed environment, then you can drive through it in a closed loop simulation. And here you can see how now, for example, in this specific case, we have fixed this issue of having a temporal inconsistency of the rendering of the grass. I think this is useful. It's not the only way, obviously, to bring together video generation with neural reconstruction engines. But I think it's a very promising direction to really get the best of both worlds and provide simulation technologies that are highly accurate from a sensor standpoint, but also generalizable in terms of what we can generate. Cool. So let's move now to how we can use foundation models as part of the onboard stack. So as I said before, foundation models have a lot of promise for driving tasks, because since they have been exposed to internet scale knowledge, in principle, they have seen everything. So they might allow us to better deal with the corner cases, or given a certain level of target performance, they might allow us to achieve the target performance with less AV-specific data, which tends to be very expensive. At least this is the hypothesis. So do we have any evidence for it? Well, in a work that we published last year at Calm, we tested this idea through work that we refer to as agent driver, where basically we view a large language model as an embodied agent that calls on demand different tasks, such as detection, forecasting, planning. So basically the language model, by using language as an interface, reasons through a driving task, calls on demand different driving modules, and then finally produces a plan that is enacted, and then we close the loop in a receding horizon fashion. Of course, this is not the way you would architect an autonomy stack, but this is more to test the potential of using large language model and vision language models as part of the driving task. In the graph in the bottom left, we show the results. So on the x-axis is the percentage of AV-specific data that is used versus what was used by, at the time, one of the best open source driving models, namely UniAD. So we see here, and on the y-axis, I represent two metrics that loosely model how well we follow a lane and how we stay out of unsafe situations. So here you can see that that agent driver, so the LLM embodied agent, with only 1% of the data already achieves performance that is better than the best available open source driving model. And there is no magic here. So how agent driver can only need 1% of the data? Well, because it's bringing to the task of driving all the knowledge that is being acquired at the internet scale. And we've seen, so this for large language models specifically, we've seen also similar promising results in the context of vision language models in another work called Dolphins. So there is potential then to use these models as part of the driving task. Then the question is, how do we best use these models as part of a driving stack? Which brings me to one of my favorite topics, that is that of system architecting. So system architecting as a topic has seen a resurgence of interest in the past, I would say, couple of years as well. So traditionally, the way that we architect in an autonomy stack is highly modular, with key modules being detection, tracking, prediction, planning, control, and so on and so on and so forth. And there are a lot of benefits to this architecture. For example, interpretability, reusability, debuggability, and so forth. But this architecture also gives rise to integration challenges and cannot be end-to-end optimized with the data. So it tends to have a relatively lower ceiling in terms of achievable performance. Because of that, about 10 years ago, people have started looking into end-to-end AV architecture, whereby loosely we have a very large model, typically a neural network, that links inputs to outputs. So this is a monolithic implementation of an end-to-end model. And of course, at least theoretically, this model can achieve a level of performance that is higher than that of a modular architecture, since it can be trained end-to-end and there are no information bottlenecks. But the buggability becomes very difficult. Establishing a safety argument for such an architecture becomes extremely difficult. And so for this reason, why it was very interesting from an academic standpoint, at least in its monolithic implementation, this idea hasn't had a lot of success. But in the past couple of years, thanks to advances in terms of new differentiable algorithms and more powerful differentiable architectures, people have been looking at the potential of bringing together these two paradigms that, from my point of view, represent the two ends of a continuum spectrum in what I refer to as a differentiable and modular AV architectures, where we still have some modules, but some modules are made differentiable so that the entire architecture can actually be trained end-to-end. But if you're interested in standing up an end-to-end modular architecture, now we have opened up a huge design space that essentially has three main dimensions. First of all, we had to decide which modules we want to account in our differentiable architecture. We have to decide on how we want to represent the information that flows across modules. Like, for example, in the case of mapping, we want to use vectorized polylines and polygons to represent lanes, or maybe just a rasterized image. And then another important dimension that has been traditionally a bit overlooked, at least in the academic literature, is that of dependencies across modules. For example, should occupancy prediction explicitly depend on motion prediction, yes or no? In order to explore this very large design space, in a paper we published last year at the CVPR, we developed a computational graph paradigm for the task of driving that allow us to make a sort of exhaustive exploration across all sorts of architectures and properly characterize the necessities of given modules, their placement, and what type of representation is most useful. I'll leave the details to the CVPR paper. There are a lot of comparative studies. Here, we just jump directly to the conclusion. So at least in the setting that was investigated in the paper, an architecture that turned out to be particularly advantageous is a so-called parallel architecture that we refer to as a para-drive. So this is an architecture whereby we have a large backbone that processes tokenized sensor information with multiple heads, representing the task of mapping, motion prediction, occupancy prediction, and motion planning. At training time, we co-train the stack by using these four key tasks. And these four key tasks are all necessary and crucial because they allow us to shape the latent space in a way that is cognizant of the task of mapping, occupancy prediction, and so on. But at inference time, we only exercise the motion planning head to produce the trajectory, which, of course, allow us to provide with a considerable computational advances because we don't have to go through all the other heads. So what we see is that this architecture is better in terms of performance, but is also significantly faster, as again compared to state-of-the-art open source driving models out there. Interestingly, some of the other heads, like for example, mapping or motion prediction, could be optionally run at runtime, perhaps at a lower update rate, for example, to provide consistency checks and monitor the health of a stack. So we have then used this parallelized architecture as a sort of an archetype for a number of investigations that I've carried out in my labs at Stanford and NVIDIA, and merged this archetype with a variety of lessons learned from the field of foundation models, particularly using a powerful internet pre-trained image tokenizer, leveraging a tokens in, tokens out architecture for the transformer backbone, and then, and this is really aligned with the paradriver concept, using scalable supervision through video generation and language generation, in addition to other AV-specific driving tasks. So one architecture we experimented with is an architecture where, in addition to the standard driving tasks, such as object detection, we also consider the task of video generation. Of course, we don't generate videos online. That wouldn't be very useful. We only do it offline as an auxiliary task to endow the model with better spatial reasoning. So we train the model with video generation as an auxiliary task. And here you can see some of the tests we perform of an in-house closed-loop simulator that relies on neural reconstruction technologies. And we see immediately that actually the model can handle pretty well unprotected left turns. Having gained confidence in this model, we deployed it on the car. And here we can see some experiments from road tests in the area of San Francisco. And we have an architecture that essentially can drive without any sort of help from a safety driver for several minutes in a very natural way. And importantly, that has been developed at a fraction of the cost that a typical modular stack would require. So, and again, there is no magic here. The magic is that we are bringing the benefit of large-scale machine learning to the task of driving. I talked about video generation. Another pre-training task we have looked into is to then look at the language pre-trained backbones. Of course, driving is a structured task, so it stands to reason that a language pre-trained model that is pre-trained on language, which in a way is a way of reasoning in a structured way through task, might be useful. Well, we do have evidence for that. Like, for example, in the plot on the right, I showed that by using a large language model pre-trained backbone, we can achieve a better performance. The x-axis represents the number of epochs for training. The y-axis is one metric we use to measure performance. The specific numbers are not too important here. The main point is that we can achieve better performance and faster, as opposed to using a backbone, an identical backbone that is trained from scratch. We were very excited about these results because this was one of the very first ones to really quantitatively show the value of using large language models for driving. And we have tested these models again in our closed loop simulator. So for example, here you can see this model reasoning zero shot about a complicated situation, like for example, driving around the construction zones. So where do we go from here? As I mentioned before, I see video generation and language generation, so these two broad classes of pre-training tasks, as a largely complementary. So I see a future whereby architectures will unify these two tasks. At the same time, of course, in the past months, there has been a lot of emphasis on reasoning models like DeepSeek and the like. So accordingly, we are also working on a number of strategies to post-train and fine-tune our model on reasoning traces to even more explicitly elicit reasoning pathways to push the boundaries of what is possible with this type of architecture. So stay tuned for more results soon. All right, let me move to the final topic, which is that of safety. So as I said, the safety, I mean, there are concerns about using AI models in a safety critical system. But my point here is that foundation models are not black magic. They are large-scale models. And of course, the automotive community, the aerospace community have a lot of experience with building large-scale machine learning models, data-driven models in safety critical stacks. And broadly, there are the three main ways to build the guardrails to keep these large-scale models in check. Design time guardrails, so these are steps we make at design time to make sure, for example, that we train the models on safe behaviors, or that we architect the system with enough redundancy and diversity so that we can decompose the safety targets and achieve the very high safety targets needed with a reasonable amount of data. Runtime guardrails. So these are mechanisms that we put in place at runtime to monitor, for example, at the input level, if the AI model is operating out of distribution, at the output level, whether the model is producing inconsistent actions through time, or, for example, to arbitrate between an end-to-end model and a more classical model, providing essentially physics-based guardrails and contingency plans. And of course, verification and validation guardrails to make sure that our system fulfills rigorous safety KPIs. Now, I could actually deliver an entire talk on this topic, and here I provide some references that you could have a look at if you're interested. But even more importantly, Jensen Huang, who is the CEO of NVIDIA, announced at the last GTC conference 2 weeks ago, NVIDIA Halos, which is a system that NVIDIA is developing to provide a safety from hardware to algorithms for safety critical applications, AV and physical AI more broadly. This system leverages several of the research results that I've been working on for the past few years. I'm very excited that it's coming all together. And if you are interested in it, so we had a full AV safety day at the GTC 2 weeks with all the presentations that are available online. So here I provide the link for it, and you can have a little bit more exposure to all the things that we're doing on the safety side. But what I want to do for the very last part of the talk is to talk a bit more on how foundation models can help with improving the safety of an autonomous vehicle. This is something that has been a little bit overlooked in the literature, specifically by focusing on the task of runtime monitoring. And to make it a little bit more grounded into something that is practical, let me show here the display of a Tesla vehicle. So here we see a lot of traffic lights that are spawned by a truck. That doesn't make any sense until you see what is happening. There is actually a truck that is transporting traffic lights that are being interpreted as a legal traffic light, and that is fooling the Tesla autopilot. So this is another case that is causing, again, trouble to a Tesla autopilot. I don't have anything, at least personally, against the Tesla autopilot. I think it's great. But since it's so commonplace, there are a lot of interesting experiences by customers that are shared on the internet. So here you see a case whereby there is a stop sign that is printed on a billboard. And when the customer goes by the billboard, every time the Tesla steps on the brakes, thereby performing a ghost braking maneuver, which is unsafe, first of all, and also very inconvenient. So I refer to this type of anomalies as a semantic anomalies. Here you can't really say that, for example, the object detector has made a mistake. There was indeed a stop sign in the scene, but the autopilot, the system didn't have enough semantic context in order to properly reason through that case. So my point here is that all that the vehicle would need in order to better handle those situations is a little bit more of a semantic understanding of a scene. And this is, again, where large language models can help. We recreated the scene with a traffic light on the truck in the Carla simulator. Here you can see that the autonomous vehicle stops by mistake again on the highway. Then we use an open vocabulary object detector to parse the scene, and the system observes that, among other things, a truck carrying a traffic light is part of the scene. And then we use this information as part of an input prompt template where, among other things, we basically tell the system what does it entail to be a runtime monitor. And the output is interesting. So the output of the large language model is that for some elements, such as a tree, there is no cause of alarm. But for the truck carrying a traffic light, this is indeed an anomaly. And it also provides an explanation for why this is an anomaly. Is it safe to drive in the presence of this vehicle? No, this could deceive the vehicle into interpreting the traffic light as a legal traffic signal. This is sort of emerging capability that is very, very useful. So this looks nice, but on the other hand, as you know, full-blown autoregressive generation of language is computationally very expensive. So then we explored the idea of how we can use this powerful tool, but in a way that is more computationally friendly. And the insight that we had is that oftentimes detecting if something is anomalous is much less complicated than deciding what to do once an anomaly is detected. You know, as humans, oftentimes when we drive, basically we don't really think, but when there is something weird or perceived as weird, we slow down to buy us some time, and then we think through on what to do next. Well, this is essentially the idea that we explored in a paper that last year received the Best Paper Award at RSS, whereby we use large language model embeddings in order to perform anomaly detection. And once an anomaly is detected, then we query a full-blown large language model, with the idea that reasoning only the level of embeddings is very fast. And if we really have to think about contingency plans, then we would need to slow down the dynamics to allow for the full generation of contingency plans. Specifically, what we do is to generate a cache of large language model embeddings for nominal scenes that have been collected at training time. And when at test time, we see a new scene, like for example, here, a stop on a billboard, we extract the embedding, we compare it to the embedding that we have in the vector database, we form a sort of distance signal, and we threshold it with a threshold that, of course, is calibrated on a test set. And then, depending on the result, we classify the scene as nominal or anomalous. And this can be done extremely quickly. But crucially, we still use large language model embeddings that still allow us to leverage the contextual knowledge that a large language model has. So this is the end result. If we use the scheme on the left, we see a driving stack that drives without our large language model reasoner as a runtime monitor, and it detects a stop sign, and then it stops by mistake. In our system, we have the large language model embedded that constantly monitors for anomalies. We see that there is something anomalous, but at this point, we query a full-blown large language model that tells us, no, there is no reason to worry about, you can keep going. Specifically, the way it works is that we first detect the anomaly with the large language model embeddings, and this can be done extremely fast, basically in a matter of a few milliseconds with very high accuracy. And then if as in this case, something anomalous is detected, then we slow down and we query GPT 3.5 in this case. Everything is orchestrated into a model predictive control scheme that account for the delay that you would incur by querying an LLM. And so the maneuver by you slow down in order to buy time is really a result of the MPC optimization. Now, here you can see that we can achieve a fairly high true positive rate and a decent false positive rate. Of course, what matters here is to err more on the side of caution. But of course, you can achieve even better accuracy if you use a higher capacity models. But of course, that is also a trade-off with respect to how much time you can afford in terms of a delay. And this is only first step. Like there are many other things that one can do in order to improve this methodology. For example, reason about multi-frame observations as opposed to just a single frame, reason about the foundation model uncertainty outputs, fine-tuning the model on AV data. Here, basically, we're using the model zero shot from OpenAI. All of this to say, though, that I think this idea of using large language models in a sort of a think fast and slow type of framework as a parallel algorithmic pipeline is also a very interesting possibility to use large language models as part of an autonomy stack. Here we tested this framework on a quadrotor that I will skip in the interest of time. If you're interested in these topics, basically auto distribution data in robotics and how to handle with it, we have a review paper. And then I will wrap it up by saying that foundation models have, as I argued in this talk, a lot of potential to provide a quantum leap in long-tail generalization for AV applications, and they have the potential to really empower the full AV program, not just the stack on the vehicle, but the full life cycle of the product. There are many different foundation models one could use. They have complementary properties, but I see a future where all these models are going to be unified. In terms of using the foundation models as part of the onboard stack, they can be used to replace existing pipelines like end-to-end or improving them, for example, by leveraging a runtime monitor. And the parallel architecture provides key opportunities to embed foundation models within a stack, as I show through a couple of examples where we use video generation and language generation as auxiliary tasks. And finally, for safety, of course, there are safety concerns, but we do have a lot of tools in order to address those concerns. But importantly, foundation models also provide key opportunities to improve the safety of autonomous vehicles. With that, I will thank all my collaborators at Stanford, at NVIDIA, and the Pavone team at NVIDIA that is working on foundation model-empowered end-to-end AV stacks. All right. Thank you, everyone.